Learn like a pro.
So, how do you take something like salty seawater and get pure, clean drinking water out of it? Well, the secret is a really cool process called simple distillation. And today, we're going to break down exactly how it works. All right, let's dive into this setup. Now, at first glance, it might look a little complicated, right? But we're going to think of it as an architecture of purification. Every single piece you see here has a very specific job to do. So let's start by looking at the blueprint. Okay, first up, the purification blueprint. The whole thing, the entire apparatus, really just boils down to 3 main functional zones. Each one is responsible for a critical step in the journey from a messy mixture to a pure liquid. And here they are, Zone 1. You can think of that as the engine room, the boiling zone. That's where the separation really kicks off. From there, the vapor travels over to Zone 2, the cooling zone, for a pretty crucial transformation. And finally, everything we want ends up right here, in Zone 3, the recovery zone, where we collect our pure stuff. This table really lays it all out for us. You can see exactly how each physical component, each piece of glassware, is tied directly to a change in the substance's state. The distillation flask, its whole job is to turn liquid into gas. The condenser, it steps in to do the exact opposite, turning that gas right back into a liquid. And the receiving flask just catches the final product. It's a beautifully simple system when you break it down like this. So, with our blueprint in mind, let's actually follow the substance on its journey. The real magic here is that the entire process hinges on forcing the substance to change its physical state, not just once, but twice. That's the secret to leaving all those impurities behind. The whole trip begins in what we can call the thermal engine. We apply heat, the liquid starts to boil, and poof, it turns into vapor and starts to rise up and away. And the key part? All the solid impurities have much higher boiling points, so they get left behind, stuck in the flask. Now check this out. This is a really key scientific principle at play. Once a pure liquid hits its boiling point, the temperature just flatlines. It stays totally constant. All that heat energy isn't making things hotter, it's being used for one thing and one thing only, changing the state from liquid to gas. And that stability, that flat line, is our guarantee that we're separating a single pure substance. Okay, so our pure vapor is on the move, and now it enters the cooling bridge. And this is where some really clever engineering comes in. Hot vapor flows through the middle tube, right? But cold water flows around it in the opposite direction. This countercurrent design is incredibly efficient, and it guarantees that the vapor condenses back into a liquid way before it has any chance to escape. So this diagram just puts it all together perfectly. It's a continuous loop driven by 2 opposite forces. Phase 1, vaporization, is powered by heat. Phase 2, condensation, is powered by cold. And it's by forcing the substance through these 2 changes, one after the other, that we get that purification. Now, the overall concept is pretty straightforward, but getting it right really comes down to the art of precision. A few small but absolutely critical details in the setup can make a huge difference in the purity and the safety of what you get at the end. Let's start with where you put the thermometer. You can't just drop it in anywhere. Notice how the bulb is positioned exactly at the mouth of the condenser? That's totally intentional. It makes sure we're measuring the temperature of the vapor at the precise moment it's about to be cooled. That's the only way to get a true reading of the boiling point. So, here's a practical problem. When you heat a liquid, sometimes it can boil way too violently all at once. It's a dangerous thing called bumping, and it can completely ruin your experiment. So how do you make sure you get a nice, smooth, gentle boil? Well, the solution is actually pretty simple. You add boiling chips. These are just little porous stones. Their rough surfaces give the bubbles something to form on. They're called nucleation sites. This lets the bubbles form gently and consistently, which prevents one of those dangerous sudden eruptions. And finally, we get to the end of the line. We've done all this work to make a pure liquid. So how do we collect it safely? Without losing all our hard work to splashing or just having it evaporate away. This is where the shape of your glassware really matters. A wide-mouthed beaker? Terrible choice. Your pure liquid can splash right out. Instead, we use a conical flask. See that narrow neck? It acts like a natural splash guard, making sure we collect every last drop. But what if our purified liquid is volatile, meaning it evaporates super easily? Well, any stray heat from our boiling flask could make it turn right back into a vapor and just disappear. The solution? We place the receiving flask in a cold water bath.
The water acts as a perfect heat shield, soaking up any extra heat and keeping our valuable liquid cool and, most importantly, liquid.
So let's recap the whole journey, shall we? Step 1, vaporize. We apply heat to separate the liquid from all the impurities. Step 2, condense. We use that super efficient countercurrent flow to turn the vapor back into a pure liquid. And step 3, collect. We use the right tools to safely capture our final product. Vaporize, condense, collect. Simple as that. So, simple distillation is an amazing tool for separating a solid from a liquid. But that brings up a new question, doesn't it? What if your mixture isn't a solid and a liquid, but two totally different liquids mixed together and each one has its own boiling point? How would you separate those? Well, that's a different kind of architectural challenge and a puzzle for another time.